Okay, so today is I'll be talking about some of the topics that we haven't discussed so far yet that are relevant generically to ALF sim or to auxiliary field Monte Carlo simulation. Specifically, I want to talk about. Okay, I don't know if one can see the cursor. I want to talk about the sign problem, what it is, where it comes from, how one can, well, kind of deal with it. And symmetries that show that there won't be a sign problem in the current simulation of the model that one is interested in. I'll be talking about stabilization, and I'm trying to give a few examples of potential pitfalls that you can run into. So let's say you have encoded correctly the Hamiltonian that you're simulating. There is no bug in the code. You use the black box of the local updates, but you still don't get the right result. How do I notice that things are going wrong, and how do I have to analyze further and potentially overcome these issues? And if time permits, I will be discussing global updates. If I'm running out of time, I might be handing over to Fakir a little bit sooner so that he can present the projects that we have in mind before for the rest of the workshop. Okay, so let's start by talking on the sign problem, and I will start with a little bit of a whiteboard discussion. So first, let's do a recap. I hope you can read this. So if people can't read this, please let me know of the crucial formulas that the algorithm is based on. We are looking at the partition function, which we rewrote as a sum over configurations. There's an interacting part which only depends on the fields. This is either the Gaussian factors for a purely fermionic interaction or the details of the bosonic part if you couple your electrons to phonons or Ising spins or something like this. And there is the fermion determinant, where we have the identity plus the product of all the B matrices, which takes this form. And it's convenient to define this whole thing here as an effective action. So we have the sum over the configurations times of e to the minus s, now without the subscript O or 0, to indicate that it includes the determinant of these configurations. And the observable that we are interested in takes the following form. As Emily showed you, we have a summation over these configurations. We have the weight e to the minus sc, depending on the configuration that you have. And then the specific contribution of a given configuration C to the observable. And of course, this has to be normalized by e to the minus sc. And let me also remind you that the observable for a given configuration was written in a form where we had the fermion trace of the operator for all these B matrices, V1 after the Trotter decomposition and Hubbard-Sartanovich transformation. And this is divided by e to the minus sc. And this division will become important during one of the pitfalls that can occur if you look at auxiliary field Monte Carlo simulations. And I think this is actually something that might occur in many Monte Carlo methods. So what is the sign problem? For this, we have to remember that when we proposed an update and we were calculating the acceptance, an update from some configuration C to some new configuration C tilde, then the rate for this acceptance R is the minimum of 1, and then I take the relative weight between them that I have e to the minus s sc tilde by e to the minus sc. And here we implicitly assume that this is a positive number so that we can treat this as a probability of accepting this move. But now you see that there is one part which is generically positive, but the determinant can be any sign. So we run into trouble when the configurations have weights where e to the minus s for an arbitrary configuration C is not positive, or to phrase it, it's not, yes, it's not positive. Or you can also phrase it the other way. If this is larger than 0 for any configuration C, then these weights are always positive. I can interpret as a probability, and there is no sign problem. So no sign problem. Before discussing conditions by which we can prove that this relation holds, let me first argue what to do when there is an actual sign problem. So I'm not assuming that this is positive. I'm not even assuming that this is real. So when we have the generic case, then we are employing a reweighting scheme. And for this, it's helpful to observe that the physical partition function C itself is real, because this is e to the minus the energies. We wrote this as a summation over the configurations of e to the minus sc, but this was an equivalence transformation. So if these terms are negative or positive, or if there are complex terms, then at least the complex part always has to cancel once I sum over all of them, because the original number was a real number. So this also implies that I can take the complex conjugation of C, and it's still the same thing. So I can also write this as e to the minus sc complex conjugate, and the sum doesn't change its value. So in other words, I can also write the partition sum C as the sum over the configurations, but here I'm not taking the full weight of the exponential, but I'm only looking at the real part of e to the minus sc. I hope this is clear. So at some point, we will be replacing this sum by this real part. But to show or to see where this occurs, we have to look at the quantities that we are really interested in, and these are the observables. So let's look at again at the observable. Let me write the formula again, that this is e to the minus sc. And then the observable for the given configuration divided by the summation over C. And up there, I still wrote that this is e to the minus sc. But here I'm making use of this relation and replace it by the real part of e to the minus sc. Maybe I can use colors. I hope this still comes through the camera for the participants online, because I want to manipulate this equation where in the enumerator, I'm essentially multiplying by a 1, but it's a special one. Namely, it's the real part of e to the minus sc divided by the real part of e to the minus sc. So this doesn't change anything, but I'm starting to approach the real part of the original weight with its normalization defining the probability of this expression. But I'm not quite done yet, because the next manipulation that I want to do, and I'm using now the fact that I'm on a whiteboard, I can introduce the absolute value of this object and multiply it by the sign of the configuration C. Maybe I should use C tilde, because these are consistent, and the C's here are different from the C's up here. And I can do the same thing here, where I now only take the absolute value of the real part and separate off the sign of the configuration. And if I look at the formula that I have generated and rearrange the terms, sorry. Okay, let me grow this formula even further. So I hope every part of this step is clear to the audience, both here and virtually, that I have only rewritten things without changing the value. And now I'm introducing yet another multiplication by 1. But it's of course not the trivial one. So now I'm introducing a sum over configurations. Let me call this one Z0, because this is again an independent configurations of all the sums that we have here. And now I'm summing over the absolute value of the real part of e to the minus sc. And this would change this overall, but if I divide both the numerator and denominator by the same number, I again haven't changed anything. S of C tilde 0 absolute value. And now we are at the stage where we can identify, we have a third color? No. Okay, let me encircle the terms that will go together. And I want to take the real part, the absolute value of the real part from here, combined with this normalization factor, and also the same thing down here, combined with this. And now I ensure that these are always positive numbers. So if I replace the weights at the end of the day by the real part of this in these formulas, I have ensured that this will be a positive number, and I can always interpret this as a probability to accept the move and not. But the price that I had to pay is that the formulas for measuring the observables became a lot more complicated. So let me write them again, where I define the reweighted probability of the configuration C, which is precisely the norm or the absolute value of the real part of the original weight normalized by this. And then I'm left with, on one hand, I have the sign of the configuration C. This is this factor. Then I have e to the minus s0 divided by the real part of e to the minus sz. And then I finally have the expectation value that we already started with here. And this was only the enumerator. Now, if I look at the denominator, I have the sign of C and the probability. So here I have a sum over C prime. I have the sign of this configuration, sorry, not C prime, C tilde. and I have the probability with a reweighting of this configuration C tilde. So we can now interpret this as this is one observable that we measure with the Monte Carlo, and this is a second observable. Because here I'm averaging the sign with the given probability. Here I'm averaging this quantity. So I can think of this as being the expectation value of the sign of e to the minus s divided by the real part of e to the minus s times the actual observable that I'm interested in. And now I have to divide this by the average value of the sign. So maybe you might think, wait a second, I said the sign problem is related to probabilities becoming complex or negative, but this is an expression where everything is positive. I can interpret everything as a probability, and the Monte Carlo seems to work. So where's the bug in the argument? For this, we have to look at the sign. And you can interpret the sign as the difference of two partition functions, namely the original partition function and the partition function after reweighting. And with a little bit of physical intuition, you can argue that the sign can be thought of as the difference of two partition functions, and the partition functions are extensive quantities, which typically have the form that there is some number, which is usually the free energy. So now when I take the ratio of two, there will be the difference of the free energy, and it's extensive. So this is the number of fermion sites and the inverse temperature, where this here is the free energy density, which would be an intensive quantity. So the price that we pay when we do this reweighting scheme is we have to divide by a number that is exponentially small. So we have to measure this exponentially small number precise enough to distinguish it from zero. Otherwise, we're dividing 0 by 0 and get noise. So to measure this number more precise than this exponential factor, we will have to invest a CPU time, since the error of an observable scales like 1 over the CPU time, which grows exponentially. The 2 is from the square root by delta NF and beta. So generically, even though we can formulate this in terms of probabilities, we still end up with an exponentially long runtime. And the problem is dividing by a noisy 0. Okay. So any questions to this? Yes.
Is it possible somehow to get a prediction of how bad the sign problem will be depending on the model?
So you can make a strong statement if you have a symmetry that guarantees that there is no sign problem, which I will discuss next. But having a feeling of if you know that the model has a sign problem, predicting how hard it is extremely difficult. Okay. And I don't have a good gut feeling.
Can I also have a question?
Yes, let's take the Zoom question first. Please go ahead.
So what is the way to interpret the sign problem in 0 temperature case when you project the trial wave function? Because then you don't have this denominator, which is this sign expectation value.
No, you would also have the enumerator with the sign, because the enumerator of the sign comes from this reweighting scheme that I separate off the phase from the sign of the configuration from the absolute value.
So the same reason. So yes. Okay, thank you.
Yes. But this also leads me to, can you repeat your question though?
Yeah, so it's essentially a follow-up of what I think you all asked, which is Is there a reasonable or quantitative way to even answer this question of how hard a sign problem is? Is there literature, do you know, of attempts to?
Yes, yes. So there is literature. Young has been working on this. And the way how I understand his works are that you essentially make use of this comparison between two partition functions.
Okay.
And one way is, for example, let's say that you know for some reason that the weights are all real. So it's not a phase problem to begin with, it's only a sign problem. Then you can always make a real number positive if you square it. So you could imagine introducing an artificial SU2 degree of freedom, which is a symmetry for each configuration. So you're looking at a different simulation, and then you can control or you can argue about the partition function of these two simulations. One that you're interested in, and the other one with an additional SU2 symmetry.
Artificial bosonic.
Yes, and he has arguments that you can guarantee the ground state will have, the two simulations will have the same ground state energy. And when they have the same ground state energy, the difference in the free energy is zero.
So you mean the polynomial sign problem?
So you get the polynomial sign problem where the ground state degeneracy matters. But this is a very special case because in most of the models, it's extremely hard to control that the two models have the same free energy, which I think is impossible, or the same ground state energy, which may work in some special cases.
And also, if I understand correctly, this difference in free energy of this measure would be basis dependent, or?
Yes, it depends on the details of your reweighting scheme. So I decided to do the reweighting scheme with the absolute value, but assuming that, or knowing that this is real, I could have done the reweighting scheme where I square it. So after squaring it, I also have a perfect, a positive number. But of course, the sign term that I have here is different.
But also, can I not imagine doing maybe some unitary transformation on the formulas before starting and the basis changes and then numbers change, right? Or you don't expect that to create a difference?
So the sign is basis dependent, but it's a basis dependence in the auxiliary fields that you introduce. And then you might want to talk to Maxime working on Lefschetz symbols and how to deform integration paths.
I mean, what you were saying is a unitary transformation. It's canonical, so the trace won't change for Hubbard-Satonovich configuration. So you don't. So you can rotate your fermions as much as you want, and nothing will change. You have to change the Hubbard-Satonovich.
Yes, right. So the unitary on the fermions doesn't make a difference.
Yeah, of course. That thing that was it.
The unitary on the auxiliary fields and finding a different. Well, it's not really a unitary. Finding a different auxiliary field decomposition can make a difference.
So I think that the thing you should imagine to try to work around or to get it. So the sign problem basically is not a problem if you can go down to energy scales which are relevant for the physics you want to do, right? So it depends on your delta, right? So it becomes an optimization problem, and then you would hope to be able to write down all the possible path integrals and to optimize over all these path integrals. But one can try to think about it, how to parameterize a path integral somewhere in some restricted things and try to do something like that. But
yeah. All right. So how do we know that there is no sign problem? So can we find a way to guarantee essentially that these determinants are positive? Because when the determinant is positive, this term is positive, there is no sign problem to begin with. And since the determinants are the product of the eigenvalues of the determinant or of the matrix, then you could guess that one way of ensuring that they are positive is if they come in pairs and that these pairs are complex conjugates of each other. This is one of the more powerful ways to show that determinants are positive. And one way that you may already be reminded, I want to have complex conjugations, I want to have pairs, so this kind of pushes you towards thinking about Gramos pairs, so that there is a time reversal symmetry. Specifically, it's an anti-unitary symmetry to have the complex conjugation. It squares to -1. for the symmetry to square to -1 is important because then you can guarantee that the two eigenstates that belong to the eigen value are actually two orthogonal states and span a two-dimensional Hilbert space, so that you don't have one state which is related to itself. Then you would only know that the eigenvalue is real, but you can't control the sign of it. So you really need a pair of eigenstates. And and then you have, when you have this time reversal symmetry, and it's important that this is a symmetry of the Hamiltonian after the Hubbard-Satonovich transformation, not beforehand, so that you can guarantee that the time reversal symmetry applies to any given field configuration. And if this is the case, then the V matrices inherit the time reversal symmetry, the product of the V matrices inherit the time reversal symmetry, this whole expression has the time reversal symmetry, and I know that the eigenvalues come in complex conjugate pairs. Actually, one cannot only use time reversal symmetry, but particle hole symmetry, even though there one has to be a little bit more careful, because the condition that the vacuum, the ground state, the vacuum of the many-body fermion state that you create is not invariant, so you need an additional U1 symmetry. But yeah, let's leave this as a side comment. There are additional developments where you can, for example, think about Majorana representations and find other symmetries, other combination of symmetries to show that these determinants are positive. There are also now discussions where you have an approximate symmetry, but it's good enough to guarantee the absence of the sign problem. But this should conclude the discussion of the sign problem, unless there are questions regarding this. Yes, there's a question in the back.
What do you mean with approximate symmetry?
I'm not sure if I can answer easily. But the question, the discussion was there that you do have one, in the Majorana basis, you have one symmetry that is a proper symmetry, and then there was a second one where I think the commutator wasn't 0, but it had to be smaller than something. I don't know the details anymore. And I'm not sure if I know a practical example where this works. In Cologne, I think he was here like some time ago. Wei, yes. Yeah.
Yeah. Sorry, Li Wei. Yes,
Yes.
yeah. He came when he came and talked here. Yeah. Yes, I remember.
But I don't remember the details to
Yeah,
say
the
much
paper's
more
still-
than that.
Some other paper's still on archive, right? Not
Yeah.
published. Which is,
think
yeah, I don't know what happened to that. Correct.
Will the sign problem be absent or just weak?
No, it was a condition for the absence of the sign problem.
It would be absent, okay.
Yes.
He's a brilliant guy. He was in Cologne, as you say, with
Yeah.
Achim Roche, I
Yeah.
think. And I think he was claiming to have the paper. So it's Wei Li or Li Wei, forget. But he was claiming to have the most complete, the biggest class, to be able to predict the biggest class of sign-free problems in this paper.
Yeah.
But did we study? I thought we studied this paper at one point. I forget.
Yeah. I mean, you can think of this is a positive condition. If you have the time reversal symmetry, you're guaranteed to be positive. Now you can start thinking of adding terms that break time reversal symmetry, but maybe they don't break it enough, so that while you broke time reversal symmetry, the determinant is still positive. But this is hard for me to think about in a more precise manner. Okay, so also looking at time, I think we should speed up a little. Let me also talk about stabilization, since this is one of the troubles, or maybe even the art of the determinantal Monte Carlo. We have these B matrices that determine the weight, that determine the Green's function. We use the Green's function to calculate the probability transition rates. But if you look at these quantities, you have exponentiated operators there. And if you think about the hopping term, for example, often you have states below and above the Fermi surface. So there are positive and negative eigenvalues in the hopping matrix T. So you generate exponentially large and small scales. And the same applies to the interaction since the auxiliary field get flipped sign. So in general, just multiplying all of these exponentiated matrices will lead to numerically unstable results. What's another way of seeing this? So let's imagine we multiply these B matrices consecutively onto an identity. And think of the identity matrix in terms of the unit vectors in the direction of your, like each column is the direction of the unit vector. So what these matrices B then can do is they're not necessarily unitary, so they can rotate the vectors, but they can also change angles and they can change the length of the vector. And if you rotate enough, at some point, you might have two vectors or basis states of the identity that were rotated so much that they are almost linearly dependent from each other. Or you could have another vector which is extremely short, so that it's hard for them to be distinguished from zero. And if any of this happens, you have essentially linearly dependent columns in your B matrix. And when you calculate the determinant, you will get zero. So you can't invert the matrix, you can't calculate the Green's functions, and the algorithm will break down. The way out of this is to do a Gram-Schmidt decomposition or QR decomposition. And the idea here is that you use these householder reflections where you search for the longest vector, the largest column in your matrix that you have after applying the B matrices, and take this as the first unit vector for your rotated basis after a given set of B matrices that you have applied. And then you continue by constructing a orthonormal basis set by always projecting the rest of these functions into the states that are orthogonal to it. So what you end up with is you rewrite this matrix U by a unitary matrix which contains the eigenvectors or these orthonormal basis sets. The D contains the length of the vectors as they were generated after multiplying all these B's. And then the V term contains the information of how they were mixing with each other and how much I had to project them onto an orthogonal subspace whenever I absorb one of these vectors. And this is reorthogonalizing this and leading to a much more stable algorithm and prevents the having linearly dependent columns in the matrix. Now, let's say you have done this for the first set of B matrices. Typically, L has to be some finite number, otherwise the scale that you generate is too large. But we have more B matrices here in the determinant. So you keep the UDV from the first stabilization. You apply the B's to the U and the U only. So you start rotating and mixing the scales again. And then keeping in mind the overall scales that was generated after the first step, you do a new UDV decomposition of this set of P matrices acting on the unitary and the scale of this. And this then combines the next UDV decomposed product of P matrices for the second stabilization point. And the length of this L, or the number of the B matrices on the time slices that we multiply, is given by NREP in the ALF code. So with this, we can make sure that we have a numerically stable way of multiplying very many exponentiated matrices with each other. And the best way of ensuring that the Green's function is stable, you should always check the info file and look at the precision of the Green matrices. If the precision is not good enough, you can decrease NREP so that you apply less B matrices before you stabilize again, and hope that this will generate a stable simulation. If this still doesn't work, you can always reduce delta tau, but this comes with additional complications. So this would conclude the stabilization part. Yes, there is a question.
I have a naive question. If there is no sign problem, let's say, can it ever be like the stabilization is always a problem? I mean, can a case arise where there is no sign problem, but the stabilization is the problem?
Okay. These two things are independent from each other. You can have a stabilization issue without having a sign problem, or you can have a sign problem without necessarily having, well, the stabilization becomes more and more severe the lower you go in temperature, because then you have more and more betas, that B matrices that you multiply. And the sign problem typically also becomes more severe if you go to low temperature. But technically, they're different from each other. Bakir, you have a comment, looks like?
We never stopped the project because of a stabilization.
Yeah. Yes.
We never stopped, I never stopped the project
Yes.
because of stabilization issues.
Yes.
So that's solved, I
Yes.
would say.
Yes. Yes. And it's solved in the following way. So if you reduce L to 1, you apply only the exponentiated operators on a single time slice. And the scale that you can produce on a single time slice is ultimately controlled by your Trotter step size delta tau. So if even for L equals 1, you can't stabilize the code, you can reduce delta tau to limit the scales that are produced on a single time slice. And they are then small enough to still resolve all the different directions and stabilize it. But going to smaller delta taus is expensive in different ways. You have more Trotter time slices that you have to sample, which is more work. And there could be autocorrelations or something else.
So I guess so you also mentioned this in your first lecture, which is what are the problems you're scared of for small Trotter test steps? Probably it's
Ask the question again after the next section.
okay. Maybe you already answered it.
Yes. So, okay. Then let me talk a bit about potential pitfalls and ask you a question right away. What's wrong with this plot? Let's say you have done a simulation. This is the data that you get. All of the data points are plotted with error bars. What's wrong with this plot?
The fluctuations are larger than error bars.
Yeah, there is an issue with the error bar. Is there one point that is particularly sticking out?
Yeah, I mean, for L equals 10, at around like minus 0.3 or so, there's one which has the correct, which seems to have the correct error bars, and the other ones seem to more like underestimate the error probably.
This one.
I mean, there's one which has a big error bar and the
Yes.
other one doesn't have.
Yes.
Yeah.
Yes.
Yes.
Yes. Well, actually, there is a bit more to it. It has a considerably larger error bar than the rest of the data, but it's also systematically above. So there is a correlation between the size of the error bar and the actual deviation from the expected curve, that if you, like, with a human eye, try to lie a somewhat smooth curve through the data. And there is a reason for this. Because what happened in this simulation is that this kept happening over and over again. You had the simulation, you could say, okay, maybe I don't have enough statistics for this data point, but I want to treat all of the data on the same footing, so I'm collecting the same amount of bins for the different parameter set that I'm changing here, which is temperature. And maybe this data point that has a large error bar right now is going down, but therefore another one could pop up. That suddenly, let's say the data point at, what is this? The red one for 3-ish, suddenly goes up in the best value and an error bar that grows to a similar extent. And this happens due to the distribution that I'm plotting here on the left, where I'm looking at the expectation value itself. This is the magnetization of a symmetry breaking order parameter, or the magnetization squared. Doesn't really matter. This applies to any observable that you can look at. And I'm simply counting how often I get the given value for a given configuration. This is the counting of these OCs for a given C, for a given configuration. And what you notice is that there is a tail towards large values of this magnetization, and the tail decays, but it decays actually fairly slowly. And if you inspect it a little bit closer, the tail decays with the power of minus 2.1. And this is a problem because for the at the heart of the Monte Carlo, we have the equation that we can sum over the different configurations and assume that this will reproduce a Gaussian distribution. So we give the mean value and the error. But for the large limit theorem, you have to ensure that the variance of the underlying distribution, the distribution of the observable, if I look at the single configuration, has a finite variance. And here we are at the border of this having a finite variance. So when we fold this more and more and average over more and more configurations, we are barely able to get to a Gaussian term. So this problem is what you see here is that there are so-called rare events that happen 1 in 10,000 events. But when they do show up, they show up with a fairly large number. And this is, in this simulation, in this data point, the red one that I've highlighted, you just picked up one of these rare events, which shoots up the expectation value and the error bar with it. So this is a sign when you see something like this, that you might be in trouble with what's known as fat tails, or rare events, or spikes is another name, how this is often or referred to. What's wrong with this data? Yes, there isn't.
Actually, I still have a question about these fat tails.
Ah, sure.
So is there a way to solve this, or is there a way to basically have something in the algorithm which notices it and tries to avoid configurations like these?
Yes, very good question. So the reason where this tail is coming from, this was the equation why I wanted to write this down again. Here we were doing a reweighting scheme where we divided by the weight of the configuration. And even if I don't have a sign problem, I know that this configuration is not negative, but I can't rule out that there are extremely low weighted configurations. So the weight can be arbitrarily low. So I'm effectively dividing by 0. This means I will have configurations that are sampled extremely rarely, but whenever I sample them, they give this large contribution because I essentially divided by 0, almost 0. So when you want to solve this, what you have to do is you have to cook up a different configuration space. So you have to change the configurations that you sample somehow by a reweighting scheme. And there is one idea that you could, for example, imagine you want to have L-trot time slices for the given temperature. So you add one more artificial time slice. And you never measure on this additional time slice, but integrate over all the configurations. And what this does is it replaces the weight that I have here by the configuration with one more time slice averaged over all of these time slice, or all of the configurations on that time slice. And if this didn't have a sign problem, I'm summing over like 100 or something contribution or configurations where none of them can be negative. So there can't be a cancellation. And the chance that all of them are this rare event goes down. But in general, it's an extremely hard problem to solve. And I'm not sure if we have tried this and how generically this works, because you also have to worry about how does this scale with system size? How does this scale with temperature? I don't know if somebody else has a comment on this.
I have one additional comment, which is along the lines of making your configuration space larger. If there is an observable you're particularly interested in, the simplest thing you can do is also extend the configuration space to include your observable in it. because then that will definitely sample those low weight configurations are no longer low weight than with the observable that you.
You can insert the condition version because you have some problem coming to.
If you have a sign problem once you put your observable, yeah, I mean, then that's an issue too. I mean, like.
Yeah.
Yeah.
Can you elaborate a bit what do you mean by inserting the observable in the configuration?
Yeah, so you have your configuration space that you're sampling right now. And then you basically double your configuration space. You have all of that with your observable inserted in as well. And then you're measuring something slightly different. You need to rewrite this again with the correct weighting to get your observable out at the end. But yeah, this is what I used for a problem, and it worked fine. But it's more expensive because it's specialized to the observable that you want, and that's just assuming you want one. When we have a generic ALF, we can get many things with the same sampling.
But would it be fair to say that we don't have a general solution for that?
No, yes, this is a fair statement. I'm not aware of a general solution.
So you can play around, you can fill around for your specific problem for a specific observable if it works out. But when we fat tails are a serious problem at the same level as a sign problem, in my opinion.
Yeah. You can kind of argue that this is a sign problem in disguise. And in this case, we were, sorry? Well, I mean, if you think about where this is coming from, is that you have configurations which are going close to zero. So let's imagine, for example, you have an SU2 symmetric Hubbard simulation where you know that the spin up and the spin down sector are identical copies from each other, and without spin orbit coupling, these two will have the same real weight. And since you square them, the real numbers become positive always. But you know that if you look for a single spin determinant, they can have either sign. So the transition from the plus sector to the minus sector has to go through the zero. And this so it's kind of related to the sign problem. And it also ensures that there is a fairly large number of configurations with arbitrarily low weight. And yeah, Maxime.
So maybe one short comment. One can actually prove a theorem that dimensionality of subspace which carries zeros of determinant, basically dimensionality of subspace where weight of configurations is zero. And this dimensionality is directly connected to power law in this fat tail. So basically, if you have domain walls, so that dimensionality of manifold which carries zeros of determinant is n-1, then at least in observables which at least in 4 fermionic observables where you have two green functions, then fat tail is basically bad enough that variance is not defined. And then if you reduce dimensionality of these manifolds with zeros of determinant, then fat tails, they become less and less severe. They distributions fall with larger power law. So this is actually direct connection between this and also one maybe particular thing which might be important, because we will discuss also global updates, is that at least in some cases global and local updates they lead to also different not power laws but different prefactors in front of this power law. So that, for example, if you do local update and then you immediately measure some local observable at the same point, then power law will be the same, but prefactor in this power law will be like 10 times smaller in comparison to the global update, when you update everything and then you measure local observable averaging over the whole configuration. So that one actually should be kind of careful with global updates, because potentially they can lead to more severe spikes in the distributions.
Yeah. So, okay. Yeah, there's more questions.
And I think at least for the special case, I think if we just put the variable into the weights and then we do the incremental method, I think the cost is really the polynomial. So I think it can.
The sign problem is about basically. I understand the cost.
I didn't understand your comment.
No, yeah, I think like the incremental method for the intermittent entropy, we just
Yeah, but you somehow put you sample your
you sample it.
But maybe this is a
but I just leave the sign. But I can just put one part. I just put the real part. Whenever I can just put the real part of the measurement into the.
But
weight.
maybe this is a discussion which is a bit too specialized for now, and we can talk about this after. We're
not indifferent to.
Yes. So let me rather get this also across. What's wrong with this plot? What's wrong with this data? If you have some coupling G and some observable that you measure and you produce something like this. Yes. Because if you have an idealized line in the background, the error is larger than what you are seeing in the best value. And one way of how this can be generated is if you have an observable that starts at some point with the random configuration you started out with, and it's off. You know that the actual result is, say, 10, but for the starting configuration, you have 100 for this observable. So the algorithm should approach the equilibration after doing many updates, and then at some point end up with an order 10 number, but it will likely approach this more or less fast. And if you start at a high value and then decay to the real value that you should see for the equilibrated configurations, your timeline could look something like this. That this is the observables that you are measuring. Some noisy curve that decays, starts at whatever, 100 and decays to 10. If I calculate the mean value here and the error bar there, this doesn't make much sense. So this is one way of getting error bars that are too large, which indicates that we are stuck in the warm-up time and we have not equilibrated from a random configuration towards this.
Everything is very correlated.
Yes.
And so there are different
Yes.
yes.
Yes. That's right. So this is one explanation. Another explanation is you are doing parallel tempering, which means you are swapping configurations between different parameter sets, which then also includes that you have correlations between the different data points, and which is a problem then also, where you have to be more careful with the error analysis. So all of these statements that I'm making are not independent from what you were doing to get there. So if you do parallel tempering, keep this in mind in interpreting why the error bars are wrong. And then let me speed up a little bit. Here, the error bars are also wrong, but now they are too small and the fluctuations that I see on the data is larger than it's supposed to be, which one explanation for this, assuming we have not done parallel tempering and all of the other things, and each of them are independent data of equal quality, that you get stuck in local minima. Sometimes the local minima is a little bit low, sometimes the local minima is a little bit above the curve, and you can't get to all of the regions in the configuration space. So in this case, both of these effects, the warm-up time, where you are not moving fast enough in configuration space, and this is related to autocorrelations. And there is a tool that we may at some point see in this workshop, the check warm-up and rebin. So let me talk briefly about this rebinning. The idea is here that you now group, say, 10 original bins into one new data point. And the hope is that thereby you effectively increase the distance between the measurements, that you are getting to less correlated data points in this Markov chain. And the error typically behaves that if you are too short, like if your rebinning is too short, the data points are correlated, you think you have more information than you actually have, and you get an error bar which is too small. You start the rebinning, you get a better handle on how much information do you actually have in your Markov chain, and the error should at some point converge. So this is one indication how you can easily test with a PyALF tool whether there is an autocorrelation problem or not. But also, this is a simulation that I took from the PyALF website. And you see that the trend is still there, that you have an increase at low rebinning, but then you also see that the error bar becomes very noisy at large rebinning factors. So this is something to keep in mind also, that there is an error on the error since we extract this from statistical data. And this is more of a real life plot for this rebinning. And here we had an insanely high amount of bins. I don't know, it's maybe like 1 million bins or something of the sort. So this was a long simulation to get to this quality of data. Since we are running terribly late, I would rather skip the global updates and hand over to Fakir for the projects, unless we should, or you have a different interest in here.
I think we should continue. We should continue, and I uploaded the projects in the Discord on
Okay.
workshop 2024. Yeah, I'm fine. We're going to go anyways. The chairman has to decide.
Okay, then let's continue with global update.
Okay, so coming back to your question, why is it problematic if you make delta tau smaller and smaller and smaller? Typically, there is some energy scale related to the fluctuations in imaginary time. And when your delta tau becomes too short, you can't flip it anymore because the auxiliary fields on neighboring time slices like to be at the same value. So if you make the time delta tau smaller and smaller and smaller, you are provoking to run at least into some origins of the autocorrelation issues. And
weirdly, when delta tau goes down, maybe the autocorrelation time goes up because of your argument, but the acceptance rate goes up. Try.
Huh. Okay.
It just tells you that it's a right thing to tell you that acceptance rate and autocorrelation time are two different things.
Yeah.
Right? I could just move that, you can accept all the time, but not move it all in configurations.
Yeah.
I guess you'd have to flip correlated blocks in the imaginary time.
Yes. So this is why we have multiple versions of global updates. You can have, I was now talking about correlations in imaginary time. You could also have correlations in real space, or an algorithm where you have to fulfill constraints between the auxiliary fields. And therefore, you can do global updates on a single time slice, which allows you to change multiple fields, but the fields have to be on the same time slice. You can also do proper global changes, where you can, in principle, change an arbitrary set of auxiliary fields. You could change all of them at once. You could change half of them. They don't have to be on the same time slice. The problem, though, is that, let's say on average, you accept 50% of a single spin flip proposal, which is typically not too bad. Now you update 10 fields. If you type in your calculator 0.5 to the power of 10, you get an extremely small number. So the larger the cluster is that you update, the lower the, like if it's a random cluster, if I randomly select 10 fields that I change to a random new value, then the chances are that the acceptance weight is so low that you effectively never accept them. So it's extremely hard to build good clusters of spins that you want to update. There is, for example, the Wolf algorithm. If you have Ising models, there are ideas where you approximate the full-blown Hamiltonian or this effective action after taking the logarithm of the determinant by an effective model, and then use some sort of neural network to train it and propose good updates. You can be creative if you find the right cluster. And the other thing, the two things that we provide with the package is launchbar dynamics and hybrid Monte Carlo, even though it's the hybrid Monte Carlo with exact forces. So it's not as performant as the full hybrid Monte Carlo implementation. For launchbar, the idea is that you introduce an artificial time, the launchbar time. You take the field configuration at a given starting point, and you integrated a differential equation in this artificial timescale, where you have to know the forces. That is essentially the derivative of the action with respect to the fields, and then it's a noisy differential equation. So you can then show if the noise fulfills certain conditions, namely that it's on average 0 and it's not correlated, then you will sample the correct distribution if you make the step size in which you integrate small. And okay, let me skip this part and just show that here's an example where we look at the expectation value of the energy. We run these launchbar updates for different step sizes in this auxiliary time, and that if you extrapolate the launchbar results, you refine the exact result known from exact diagonalization, for example. But even here, you have to be a little bit careful, because this action S that I introduced is essentially the logarithm of the determinant. And I just argued that it can happen that these weights can go to 0. So if you take the logarithm, you get divergent domain walls. And the same arguments or maybe in some of these HMC talks that Peter will be giving later, this will be discussed in more detail, but they can act like domain walls so that you can't get from one region of configuration space to another. And I know that I'm brief, and this will be even shorter. For hybrid Monte Carlo, the idea is you take the original action, the original weight S here, and you supplement this with conjugate momenta, so that you have a Gaussian in the additional momenta, such that the observable, which was originally given as the integral over all the fields times the weight, and this weight or basis-dependent quantity contribution of the field, can now be written as this term, where we have an additional Gaussian integration in P, which is also part in the normalization. And now we are sampling not only the auxiliary fields that we started with, but we are sampling this larger distribution where we have the momenta and the original auxiliary fields, by again using the equations of motion. Like, we interpret this as a Hamiltonian and change the momenta by the derivative with respect to the field, while the field changes by the derivative with respect to the momenta up to the minus sign. And as long as we preserve the energy of this artificial Hamiltonian, we can generate updates for this auxiliary field S, where in general we can change every value of this or every field at the same time. And as long as we preserve the energy, this would be a global update with acceptance rate 1. But you can also have trouble if there's, say, domain walls again, because of divergent forces. And this was very brief in the end. If you are more interested in global updates, there's a more extensive section in the documentation. Other than that, I would be done with these 4 topics and conclude the presentation of determinantal Monte Carlo. Okay, are there any further questions?
So I noticed from the other QMC that if I lower the delta tau, the sign problem could be worse. For example, for like the Hubbard model, is that also the case for the ALF?
Fakir is nodding. I haven't tried. I don't know.
It's a small effect if I remember well, but if the delta tau goes down, the sign goes down. The delta tau goes. I know because we tried once, and our former friend Sandro was very excited about that. Said, "Let's do huge delta taus, and we'll solve the sign problem."
Huge delta tau, extrapolate delta tau, and be done. Yeah.
Cool.
I would also have a question. When you have shown what are the conditions to not having a sign problem that haven't depended on the lattice. In that case, everything which works on the square lattice should work on the Kagome or on the triangle lattices which are frustrated.
Good question. Excellent question. So it depends. So if you have an attractive interaction and you can use time reversal symmetry, the time reversal symmetry is typically less sensitive to the details of the lattice. And you could do an attractive Hubbard interaction on the square lattice, but I don't see a reason why not to do it on a triangular lattice.
Sorry, what has to do time reversal symmetry with the lattice structure? I mean,
yes, because for the time reversal symmetry, you do the transformation locally, and you do this with the same phase typically with the same phase for all the signs. Where the lattice and the bipartiteness of the lattice matters is if I want to use particle hole symmetry. Because for the particle hole symmetry, I want to preserve the hopping term, where I hop from one side to the other. But if I do particle hole transformation and send C to C dagger, I have to exchange them and pick up a minus sign.
Oh.
So what you typically then have to do to keep this a symmetry is you have to give some sets of sides a positive sign in the transformation and the other set of sides a negative sign, such that the faces on all bonds cancel. So this is the bipartiteness. If I have a bipartite lattice, I can have the particle hole transformation and on sublattice A with a positive sign, on the sublattice B with a negative sign, and as long as all the hopping terms are between the two sublattices, I can absorb the sign that I get from the Fermion statistics. So this, for example, rules out chemical potential to be introduced for the square lattice Hubbard model with repulsive interactions, but it also tells us that for the Kagome lattice, we will have a sign problem for repulsive density interactions. So the message is that the bipartiteness or not bipartiteness is important for particle hole symmetry. It's less important for time reversal symmetry. Probably not important.
But in that case, I don't see why is the repulsive Hubbard model not time reversal symmetric? I mean,
the reason is that the symmetry has to be there after the Hubbard-Swartanovich transformation.
I see.
And there you pick up the square root of minus delta tau u. So depending on the sign of u, you get a real square root or an imaginary square root. And this tells you how you have to absorb the sign in the transformation of the operator.
So I guess on the triangular lattice, it is the same as on the Kagome.
Yes. So for the repulsive Hubbard interaction, you need a particle hole symmetry. And the particle hole symmetry to hold for the hopping term, you have to have a bipartite lattice. And neither the triangle nor Kagome are bipartite.
Okay, thank you.
Are there any more questions? Okay, if not, then let's thank Johannes again for the very nice lecture.